Greetings, welcome to W5U3 Instruction for Engineering Design Thinking Part 1. In the earlier unit, we understood transactional model of direct instruction. The outcome for this unit is understand some aspects of instruction for engineering design thinking. Let us see what is the relation between engineering and design, or the role or the place of design in engineering. Many views exist on what engineering itself is and what design is. Engineering, the concept of engineering, how it differs from science, etc., is discussed in the related NPTEL course OBEA, Outcome Based Education and Accreditation. A view quite relevant for this unit on engineering design thinking is provided by Shepard. He says engineers scope, generate, evaluate and realize ideas. There are three key activities: scope, generate, evaluate, and then the final activity realize. So, it captures the essence of engineering design process: creation, that is scoping and generation; assessment and selection, that is evaluation; making or bringing to life the ideas, that is the realization. All these are captured in this idea of engineering design by Shepard. Design in a major sense is the essence of engineering. It begins with the identification of a need and ends with a product or system in the hands of a user. So much so that many consider design to be the essence of engineering. It is primarily concerned with synthesis rather than analysis, which is central to engineering science part. The analysis is the central aspect of engineering science part, whereas design is primarily concerned with synthesis. Design, as we mentioned, in a way defines engineering. It is an engineer's job to create new things to improve society. It is the university's obligation, that is faculty's obligation, to give students fundamental education in design. Engineering design is a systematic, intelligent process in which designers generate, evaluate and specify concepts for devices. Notice the word concepts. This is quite different from the way concept is used in the revised Bloom's taxonomy. Okay? We will discuss that. So, concepts for devices, systems or processes whose form and function achieve client's objectives. That is another key feature of design. A client's objectives or user's needs, client or user, while satisfying a specified set of constraints. This is by Clive Dime. The word concept, as I just now mentioned, in the above context means specifying the functionality or the use to which the device or system is to be put. This meaning is different from the way we use it in Bloom's taxonomy. Design problems reflect the fact that the designer has a client or customer, who in turn has in mind a set of users, the ultimate users. They can also call them as customers, for whose benefit the designed artifact is being developed. This is a key aspect of the design in the context of engineering. The design process itself is a complex cognitive process. Generally, design is generally considered difficult to learn and much more universally considered difficult to teach. Design thinking reflects the complex cognitive processes of inquiry and learning that designers engage in while developing solutions. And teaching all these processes is really a challenge for the faculty. The term design thinking was first introduced by Peter J. Rowe in his book titled Design Thinking, which was published way back in 1987. The focus of his book is design thinking in architecture and urban planning, not directly engineering, but in architecture and urban planning, similar to the origin of patterns in design, which also arose in the context of architecture. Design thinking in the specific context of engineering design is now accepted as an integral and necessary component of all engineering curricula. CDIO initiative of MIT is one often quoted example. Of course, this initiative has become now an independent organization itself: conceive, design, implement, operate. So, that initiative of MIT also recognized this idea of centrality of design in engineering. Now, it is a worldwide organization, CDIO. Several program outcomes specified by NBA refer to competencies that are directly related to engineering design. The designers perform in a systems context, making decisions as they proceed, working collaboratively in a social process, and speaking several languages with each other. When we say speaking, we mean we use those languages in the communication process. So, in a very broad sense. Instruction to facilitate these competencies is itself a complex design activity. We need to design such instruction. So, what are the key features of engineering design thinking? These are some of the key features. There are many more. We will discuss a couple of more as we move along. This is adapted from Engineering Design Thinking, Teaching and Learning by Dime et al. Some of these key features are generative questions, systems thinking, uncertainty, design decision choices, teamwork, visualization, creativity, communication in design languages. We will discuss all these features in brief, of course, in the coming slides. Generative questions. Traditional engineering courses invite deep reasoning questions, and the answers must converge to a true answers in the relevant knowledge domain. So, the objective of the questions is to arrive at truth. The objective of the questions is to arrive at the true answers. So, this assumes that there is one such true answer and we must reach there. So, that is the traditional engineering courses approach to questions. There is one specific true answer and the questions and guidance is towards reaching that one single unique true answer. By contrast, questions that arise during design thinking are exploratory in nature. We are not yet really sure what the solution should be. So, the questions that arise are exploratory in nature and their objectives are not true answers, but additional ideas and intents of the customer. So, we would like to know more, the designers would like to know more about the context in which the design and development has to take place, the background of the customers, their requirements, their unspecified intentions or desires. So, these are all the things which need to be explored. Often customers themselves may not be able to very precisely or accurately specify what they want. They may not be that clear or articulate about their own requirements. The questions are to explore all these issues. So, they are useful for framing the solution space. So, the objective of the questions during the design thinking are quite different from the objective of the questions during the regular conventional engineering courses on analysis. Generally, these two types of thinking are called convergent thinking and divergent thinking respectively. That is, when the objective of the questions is to arrive at a true answer, we say it is a convergent thinking. When the objective is to explore the design spaces, the thinking is called as divergent thinking. Here there is no idea that we should arrive at anything like a true answer. Teaching divergent inquiry in engineering thinking, in design thinking, is generally not addressed in regular engineering curricula. Most of the conventional courses encourage the convergent thinking, promote questions along those lines, and expect the students also to become good at arriving at such unique answers. The assessment is also based on the students giving such a unique answer as the response to a question. So, case study based group discussions may help students in learning to ask generative questions. Interaction with real clients where possible and subsequent guidance from instructors would be of great help. In divergent thinking, role play simulation games also would help. Institutes must consciously plan for such activities. That is generative thinking. Another key idea which is related to that is systems thinking. Engineering systems are increasingly becoming more ambitious and more complex. Further, program outcomes of NBA require designers to consider issues related to environment, sustainability, society, etc. So, which means that the systems are really becoming multi-dimensional, multi-faceted, and finding solutions in such a context would require enormous change in the mindset of the designers. So, instructing in systems thinking, the students must be trained in several different novel areas. Anticipate the possibly unintended consequences emerging from interactions among the multiple parts of a system and interactions between the system and the environment. The parts might have been designed with certain intent and they are expected to interact in some particular way to achieve some intended outcome. But in the process of becoming a system, they might interact in totally unanticipated, unintended ways, and the consequences might be really not planned at all. So, unintended consequences emerge from the interactions among the multiple parts of the system and the interactions between system and the environment also. So, students must be able to anticipate that such things are possible and then plan accordingly. Deal with incomplete information, ambiguous goals and approximate models. Textbook problems always provide complete information, the goals are clear and the models are exact. If required, for example, using ideas like linearization. But in real world, we have to deal with incomplete information, ambiguous goals and quite often approximate models. Students must be trained to handle uncertainty, must be able to think statistically, and students must be trained to make rough estimates of physical quantities in a given context, both for sanity checks and for figuring out the parameters that can be ignored safely. In several places, if you just think of that as a mathematical equation and come with an answer and think that that answer is acceptable, it may be a wrong approach. You need to do some sanity checks. For that, the engineers must have some very rough ballpark figures that he or she can come up with, which can be used for sanity checking. So, students must be trained to make rough estimates of physical quantities. As a lighter vein, you could ask your student to name two places that the students are familiar with and ask them approximately what is the distance between those two places in terms of number of feet or number of centimeters, whatever you wish to call, just a rough guess estimate. So, that kind of thinking must develop in the students. Design suitable experiments when required. The students may have to design suitable experiments when required to get data, to validate a design idea, all these things. So, all these things must be taught, or the students must be trained in all these areas. There are many other issues related to the same systems thinking kind of a context. Students must be trained to work in multidisciplinary, multicultural teams, which is the reality today. Communicate using the appropriate design languages. That could be simply text in a given language, or they could be graphical representations, drawings according to certain standards, mathematical or analytical models. There could be a variety of ways in which the design ideas are communicated. So, we could call them as design languages. So, the students must become comfortable with communicating using such diverse design languages. Make design decision choices. Notice that most of the time the choices are not between right and wrong. That is very clear. This solution is a wrong solution. Students can generally figure out very well after a certain amount of training. And this solution is right, that is also very clear. So, really the choice is not between right and wrong, but often the design choice is between right and right. Both the solutions are right, but one solution is to be preferred and implemented rather than the other solution. Why? What kind of contextual factors, what kind of constraints, what kind of aesthetics go into such design choices. So, students must be trained to make such design decision choices, often between right and right. Of course, sometimes it can be between right and wrong, but more often it is between right and right. Estimate the resources required, including human resources, costs and schedules. So, what are the possible approaches for instruction for design thinking? It can be project based instruction, problem based instruction, simulation based instruction. We have discussed their use earlier. Experiential approach to instruction, yes, we discussed that. As discussed in earlier units, the most popular approach for design thinking in engineering curricula was and continues to be project based approach to instruction. That is still the most popular approach. Design program curricula. Traditionally, engineering program curricula included a major project work, generally called as capstone project by some people, in the final year or final semester, and this was the first and only opportunity provided to the students to engage with engineering design activity. Of course, now the scenario has changed, but for quite some time that was the traditional approach. Some programs, most notably mechanical engineering and civil engineering programs, did include a core course, often a theory only course on design in earlier semesters. As I mentioned, this was the earlier scenario, but recent changes in AICTE guidelines do require students to participate in internships, but there are still implementation challenges in many institutes. So, in institutes where they are following the AICTE guidelines and providing an opportunity for the students to participate in internships, they do get a feel for the design activities. The main project in the final year is really valuable, but if that is the only activity that the students engage in terms of design, it appears too late in the scheme. Of course, recognizing that only, AICTE is suggesting that students be given an opportunities for internship, given opportunities for engaging in mini project designs, etc. So, more favored approach currently is to provide design experience to the students in the first year itself, very first year of engineering. An independent design thinking course, probably with just one unit of laboratory work or its equivalent in the National Credit Framework, the equivalent amount of students' time, or perhaps equivalent of 2 units of laboratory work, is introduced in the first year using project based approach to instruction. So, sometimes it is also called as cornerstone project. The final year project is generally called as capstone. This kind of first year projects are called as cornerstone projects. Instructor must provide considerable didactic instruction to address the issues discussed already regarding design thinking. So, the challenges of engineering design in the first year are, because these are present even in final year projects, but are more severe with the first year projects. Initial problem statement, final formulation of the problem for first year students, multidisciplinary team formation, still the students are in different departments, and the possibility of forming effective multidisciplinary teams can become quite a challenge when they are in the first year. Competencies, the concepts, tools, attitude of the first year students can be challenged. Design process to be used, students are not yet introduced to any specific design frameworks. Certain preliminary aspects of the design process need to be made available to the students. So, some kind of a scaffolding we can say. Then load on faculty, the amount of effort that the faculty have to spend to make the first year students succeed in the project work in the very first year is quite high. So, as I mentioned, the scaffolding load can be quite high for the instructors. Then assessment, finished work and compliance to the process, we need to assess both the finished work and compliance to the process. Individual contribution as well as the team contribution, they need to be evaluated. So, rubrics need to be developed. These possible rubrics are discussed further in later units. The usual approach is initial minimal direct instruction of theory and tools. What is essential is provided to the students. Close mentoring during problem formulation stage. Guidance reduced progressively, as we just discussed in earlier unit, scaffolding. Load on faculty remains an issue to be resolved at the institute level. All said and done, the faculty load can become quite high. So, at the institute level, some policy decisions as well as support are required. Another approach being tried in some institute is initial minimum direct instruction of theory and tools, about 2 weeks. A small project assigned by the faculty to provide a basis for learning the design tools, say about 4 weeks. Then a small project in reverse engineering, perhaps about 3 weeks. We will discuss reverse engineering also in the next unit. A main design project for a real or a role play client, about 6 weeks. This seems to be working well, but the main challenge again is the load on the faculty. Despite all these challenges, a design project in first year is becoming increasingly popular, as the advantages are considered to be very significant by all the stakeholders. And in fact, the AICTE guidelines, the NEP guidelines, they all encourage such innovations. Major advantages are: enhances student interest in engineering, motivates better learning in higher semesters. The initial exposure lays a strong foundation for the students to become adept at design thinking, and this helps them in the higher semesters, leads to better performance obviously in the final year project itself. Engineering design can also happen in second and third years. Student engagements in final year is quite traditional, first year is quite innovative, but it can also happen in second and third years. So, many institutes in fact are experimenting with design activities in second year or third year or both. Advantages are clear, but providing the necessary resources can be quite a challenge. Institutes need to experiment and decide on what is best for them and their students. Maybe mini projects worth certain credit requirements, or a mini project integrated with a theory course. There are several approaches possible to bring in the ideas and experience of engineering design in second and third years. The institute, the faculty and the students must work together and see what is the best way to approach the issue of promoting engineering design thinking. In the next unit, we will understand some additional aspects of instruction for engineering design thinking. Some aspects we discussed in this unit. In the next unit, we will continue discussing some more issues of engineering design thinking. Thank you. We will meet again in the next unit. Thank you.